Good day once again, students at home. We are going to talk about solid materials today. Solid materials. Solid materials. We're going to talk about solid materials today. And our first topic in solid material is going to be the deformation of solid. You already know what solids are from your key stage 3, grade 7, 8, and 10. And you have already also, you have the knowledge of solid, liquid, and gases in your IGCSE, GCSE, or O-level physics. Today we are going to go deeper into solid. So let's look at the deformation of solid. When a force is applied to a solid, the solid will be deformed. The solid will be deformed. What then happens to this solid when the force is removed? Depends on the type of solid and the amount of force applied to the solid. Some solids, for example, you have a rubber band and you pull it apart. You have changed the shape of that rubber band. When you release it, what happens to it? You can try this at home. Just slight amount of pulling. This is called tensile force. You release it. Then what happens to it? You will agree with me that your rubber band or the elastic band will return back to its what? Original shape. Take another example. Chew some gum, chewing gum. Many of you do this. And bring it out from your mouth. Apply the same amount of force you apply to your rubber band and leave it. What do you see? Does it return back to its original shape? No, you don't get it back to its original shape. So, two things here. You apply the same amount of force to substance 1, a rubber band or elastic band. You release it, you release the force. Then, when there is no more stretching force, then the elastic band returns back to its original shape. Do the same thing, same amount of force, same length of your chewing gum. You just chew a little, chew it and bring it out and pull it apart with the same amount of force, release the force, and what happens? Does it return to its original shape? No. So this brings us to two types of deformation. We're talking about deformation. You deform a particular solid. When you remove the deforming force, the solid returns back to its original shape. You deformed another solid. When you remove the deforming force, same amount of force, the material does not come back to its original shape. This brings us to the two types of deformation we have. So, let us look at the force you apply. The force you apply to this material may be a tensile force, you know the meaning of this, that is pulling force, stretching force. And it may be a compressive force to deform the solid, that is squashing or squeezing force. The force you will apply to deform this solid may be a squeezing force or stretching force. A squeezing force is called compressive force, and a stretching force is called tensile force. So, any of these you apply to the material will be deformed. This solid material being deformed, is it being deformed and returning back to its original shape when you remove the force? Or, when you remove the force, does it remain where it is now without going back to its original shape? These are the two types of deformation we have. When the body returns back to its original shape when you remove its stretching or compressive force, then you see that type of deformation is elastic deformation. You pull it or you compress it, it changes shape. And when you release the force, you remove the force, it comes back to the original shape. That type of deformation is known as elastic deformation. Elastic deformation. Again, when you stretch a material, you release the material, you release the force, and when you stretch it, there is change of shape. You release it, the force, and it comes back to the original shape. You have deformed the material elastically. This is elastic deformation, and you say the material is elastic in nature. However, if you apply a force, stretching or compressive, tensile or compressive force, tensile or compressive force, tensile or compressive, and the body no longer, when you remove the force and the body no longer returns to its original position, its original shape, you say that body has undergone plastic deformation. Plastic deformation. And you say the body is plastic in nature. The body is plastic in nature. So you write this down. Deformation of solids. A solid gets deformed upon the application of a force. You agree with that? I just told you that. This force may be a tensile force. Of course, I just told you that. Pulling force. That is stretching force. Or a compressive force. Or a compressive force. Pause your system and write this. Tensile force. This is a stretching force pulling at opposite ends of a component or material. A component may be just one part of a big body. That's a component of the body or the whole material. So that's why I said this is a stretching force pulling at opposite ends of a component or structure. This may be a component, may be a structure. I'm pulling it here, I'm pulling it here, I'm pulling at opposite ends. It may be my arm, somebody's pulling it here, somebody's pulling it here. Part of my arm, somebody's pulling it here, somebody's pulling it here. So, that is pulling at opposite ends of the whole structure or just component of the structure. It may be only my lower arm or upper arm. Upper arm, somebody pulling here, somebody pulling here at opposite ends. So, look at this. Stretching force is equals to tension. Stretching force is tension. And compressive force is a squeezing force pushing at opposite ends of the component or structure. Compression equals to squeezing force. Compression is squeezing force or compressive force. Compressive force is squeezing force. Compressive force is squeezing force or compression. So you pull it there, you push it and push it, you squeeze it together. Either compression or tensile force, compressive or tensile force applied to a body to change the shape of the body. What does the body now come out with when you remove the force? It is either going to be elastic deformation. So your deformation is either elastic or plastic. I hope you wrote the last page. It's either elastic deformation or plastic deformation. This is very common in your exams, in your AS exam. So if it is elastic deformation, this is the type of deformation in which the application of a force causes a body to change shape but returns to its original shape as soon as the deforming force is removed. When the deforming force is removed, when the force that causes the change of shape is removed, then the body returns to its original shape. This is called elastic deformation. What then happens? In the molecular level, let's look at what happens in the molecular level of the solid. Let's assume I'm pulling this solid apart. I'm pulling it apart. So, pulling at both ends. So what happens at the molecular level? It is a solid. The molecules of solid are well arranged in an organized manner, with, of course, force of attraction very high between the molecules or between the particles. A particle may be molecule, it may be ion, and it may be atoms. You remember that from your chemistry. A particle, when you say particles of matter, may be what? Maybe ion, maybe what? Maybe molecules, and it may be what? Atoms. So let's look at these molecules. If this is the material as a whole, so we have just shown a straight arrangement of the molecules. These white things here are the forces of attraction between the molecules. Force of attraction exists between the molecules. When you get later in your chemistry, we're going to talk about these forces of attraction between these molecules. There are many of them: hydrogen bond, van der Waals forces, and all those things. Okay, let's see van der Waals force. Forget about that for now. That is chemistry. Let's look at this. So when you pull, when you apply a force and pull at opposite ends of this same material, the force of attraction between the particles stretch. Don't forget the particles vibrating. From your IGCSE physics, the particles vibrate at equilibrium position, about an equilibrium position at a fixed point. When you stretch, the particles will change their equilibrium position because the force of attraction between them, represented by these white lines, will also stretch. We pull the force of attraction apart. So when you remove the stretching forces again, then this force of attraction will pull them back to the original equilibrium position. When you stretch, force of attraction, you pull the force of attraction between the particles, so the particles attain a new equilibrium position and more separation between the particles. When you remove the force, this force of attraction between the molecules or the particles pulls the particles back to their old equilibrium position. Then it becomes what it used to be. That is the molecular level. So if you are asked to explain, to talk about elastic deformation, it is better for you to talk about all this, to write all this. And you don't have to draw this, but you need to write this sometimes, depending on the mark. At the molecular level, when the body is stretched, the force of attraction between its molecules or particles are pulled apart, and the molecules move away from their equilibrium position. On removing the tensile force, the force of attraction between the particles of the solid return to their original length, causing the particle or molecules to return to their original equilibrium position, and the material as a whole return to its original shape. So the body is said to be elastic in nature. You need to write this at the molecular level also. Write it depending on the mark you have for this. It sometimes may be 3 marks. So if it's 3 marks, you have already written its change shape and it return to its original shape. If you are able to write this, it will be good for you at the molecular level. To be good for you. Then let's look at plastic deformation. For plastic deformation, this is a type of deformation in which the application of a force causes a body to change shape permanently without returning to, like the chewing gum, to its original shape, even when the deforming force is removed. Even when the deforming force is removed, the body does not return back to its original shape. You need to write this down. You already know about this, like your chewing gum. So at the molecular level, what happens? At the molecular level, what happens? When you stretch the body, you stretch it, and depending on the type of body and depending on the amount of force you have applied in certain bodies, but some bodies, so you see the force of attraction between the particles or the molecules breaking. You have broken the force of attraction between the particles or the molecules, so that when you remove the force, there is no more force of attraction to bring the particles back to their original shape or original equilibrium position. Now you stretch, you broke there are 10 new equilibrium position, the force is stretched and broken. At 10 new equilibrium position, when you release the force, no more coming back to the old equilibrium position, because you have already destroyed the force of attraction. So no force of attraction to bring the particles back to their old equilibrium position. So you will now write that down. So plastic deformation, this is the type of deformation in which the application of a force causes a body to change shape permanently without returning to its original shape, even when the deforming force is removed. That's the first part of it. That will give you some marks. At the molecular level, when the body is stretched upon the application of a force, the force of attraction between its molecules stretch and break. So the forces of attraction between its molecules stretch and break, okay, as the molecules move to new equilibrium positions. As the molecules move to new equilibrium position upon the removal of the force. Upon the removal of the force, what happens? The molecules remain in their new equilibrium positions as there are no forces to pull them back to their original equilibrium position. Hence, the body as a whole remains permanently deformed. So, the body is said to be plastic in nature. So, you write this from here, page number 2, page number 3, and if you want to help yourself further, you can draw this, but you don't need it in an exam. You can draw this, but you don't need it in an exam. It's just for you to understand. This is elastic deformation, and this is plastic deformation. So you have seen what we mean by deformation of solid. Now let us move to Hooke's law. Hooke's law is the new thing for us now after this deformation. Hooke's law. You have done this in your IGCSE, GCSE, or O level. You see, Hooke's law is talking about the stretching of a spring or wire. A spring or just one long ordinary wire, just one length of wire. So, what does it state? Hooke's law, you remember, states that when you add a force of 2 Newton to a spring, if it extends by 1 centimeter, if you add 4 Newton, Mr. Hooks is saying it should extend by 2 centimeter. If you add 6 Newtons, it should extend by 3 centimeter. If you add 8 Newton, it should extend by 4 centimeter. If you add 10 Newtons, it should extend by 5 centimeter. That means every 2 Newtons you apply, it should extend by 1 centimeter. That means it obeys Hooke's law. That means 0 Newton will extend it by nothing, by 0 centimeter. So Mr. Hooks now told us, after he has checked this experimentally and he has confirmed that this is really true for every spring or a piece of wire or a piece of metal, he says the extension, you can see every 2 centimeter is giving us the same amount, every 2 Newtons is giving us the same amount of extension in the spring. So it states that the extension in a spring or wire is directly proportional to the applied force. To the applied force. It didn't stop there, because in his experiment it continued until a point is reached where this proportionality stopped, where the material, even when you add something, is no longer proportional. It's no longer proportional. So it causes the limit of proportionality. The limit of proportionality. After that point, it is no longer proportional. It is no longer proportional. So it says the extent, Hooke's law states that the extension in a material or in a wire or in a spring or wire, the extension in a spring or wire is directly proportional. The extension in a spring or wire is directly proportional to the applied force, provided only if you do not exceed a limit. What is that limit? Limit of proportionality. Limit of proportionality. Limit of proportionality. Do not call it elastic limit. This is AS. Do not call it elastic limit. You call it provided the limit of proportionality is not exceeded. Provided this limit of proportionality is not exceeded. You do not pass the limit of proportionality. So Hooke's law state that the extension in a wire or spring is directly proportional to the applied force, provided the limit of proportionality is not exceeded. In your IGCSE is sometimes you say provided the elastic limit is not exceeded. We are going to tell you now not to write elastic limit. So, and we'll come back to this. If the force of pulling it, F, from your mathematics is directly proportional to the applied force, to the extension, which is either for IGCS, for Edexcel, you write it as delta X. For Cambridge, you write it as E. It doesn't matter. Either you write it as E or delta X, we're talking about the same thing. So for Cambridge student, you write it as like this. So if F therefore mathematically will be equal to K delta X for EdXL students, and Cambridge students, they use this notation F equals to K E, because you have to write this when you are changing this into equals to K. So this is then K will be equals to F divided by change of length, which is extension, or F as in Cambridge student, you see K equals to F divided by E. So if K equals to F over delta X here, or K equals to F over E here, this is for EdXL student, and that is for Cambridge student. EdXL student will normally represent it like this. If it is represented like this, you have no problem. But so that some of you, if you see it in your exam, we know we are talking about the same thing. The Cambridge represent it like this, and EdXL represent it like that. No, we are talking about the same thing. If we have this, this will tell you that if I write that K is a constant, that means anytime I divide F by delta X, I will always get a constant value for a particular material, for a particular piece of material, for a particular piece of a sample of a particular material, for a particular sample of a material. So I will always get F divided by delta X, I will always get K. So if that is the case, let me now say if I divide F by delta X, in my first instance, F1 delta X will be delta X1. It should be equal to, if I do the same thing by changing the force, I'll get the delta X, another delta X. So let's say F2 divided by delta X2. So I will always get the same answer. So F3 divided by delta X3. So this formula also works. This formula works, and this formula also works. So F1 divided by delta X1 equals to F2 divided by delta X2, and in this case this formula works, and I can write it as F1 divided by E1 equals to F2 divided by E2. Since it's always constant, I will always get the same answer if I divide F, the force, apply force by the word, by the extension, I will always get the same force and the same answer, which is that K. What does it really stand for? What is K really standing for here? What is our K really standing for here? The K is standing for one thing. If it is a wire, you say it is the stiffness of the wire. If it's a spring, you say it is the spring constant. Spring constant. K is either stiffness of that sample we are talking about, or if it's a spring, we say it is the spring constant. Spring constant, or the stiffness of the spring. Spring constant or stiffness of the spring. What we are saying now here is that since K equals to F divided by extension, delta X or E, if I have a very a spring that is so tough so difficult to pull apart, to change the shape, that means I apply a very large amount of force, but it extends just a little. That means it is very stiff. The stiffness is high. So yeah, a very stiff spring or wire with what? A very large amount of force will give small extension. And mathematically, if you divide a very big F by a small denominator here, you get this one to be big. So that means to say the body is very stiff. The body is very stiff. So this is stiffness for you. You can use any of the formula. You use this formula to get stiffness. And when you are looking for maybe F1 is given to you, F2 is not given to you, and you know the extension, so they're asking you this, you can get any of them. You can use this formula also. So if we draw the graph of force against extension, if you draw the graph of force against extension, I have force here in Newton, and I have extension here, my delta X or E, if it's Cambridge, of course, in meters. It's either this or this, depending on which exam you are writing. F against delta X or F against E. So you don't write both of them. So now we are going to get a straight line graph up to a particular point. Assuming we get a straight line up to this point, after which the line starts changing, let me just assume this shape, after which the line starts changing. So you can see that I have my straight line up to this point. Then the line starts changing. So my straight line, surely I know it's up to this point. So that after that point, it is no longer straight. You agree with me? If it's straight, it's supposed to continue to go like this. But it's no longer straight after that point. It's no longer straight. So if it's straight, it's supposed to be going like this. So because it has reached a limit where it is no longer proportional. So we call that place after which is no longer proportional. It is proportional up to that limit. So we call that place P, limit of proportionality. Limit of proportionality. P, limit of proportionality. Limit of proportionality. Yes, it is no longer proportional. However, it is still elastic. It is still elastic. If I pull it even past that place and I release it, it will still come back to its original shape. After P. However, a point will be reached where if I pull it past a particular point after this, it will still come back to its original shape. But there's a point here, let's assume, called E, which you know that is called the elastic limit. At elastic limit, before the elastic limit, even after P, between P and E, it is no longer proportional, but it's still elastic. Elastic means it will come back to its original shape. It is no longer proportional, but it is still elastic. I will no longer get the same increment if I had the same amount of force to my wire or to my spring. However, I will still get what? I will still be able to return it to its original shape when I remove the whole force. So, beyond E, after E, I will no longer get it to be what? Proportional. Elastic. It is no longer elastic after point E. It's no longer elastic. So, it will no longer be elastic after the point E. It is no longer elastic. So, I call that E. It is no longer elastic after point E. So, we say if it's no longer elastic beyond E, what has it become? Then it has become plastic. So E equals to elastic limit. Again, at the limit of proportionality, yes, it is still elastic, but it is no longer proportional. But after, between P and E, it is elastic, but not proportional. Between PE, elastic, but not proportional. Beyond E, it is neither elastic nor proportional, then it becomes plastic. Become plastic. It is no longer elastic and it is no longer proportional, then we say it becomes plastic. From OE in OP, it is both elastic and proportional. both elastic and proportional. Both elastic and proportional, and that place obeys Hooke's law. It obeys Hooke's law. That is the part that obeys Hooke's law. Obeys Hooke's law. That is the part OP that obeys Hooke's law. So beyond that part, it is no longer proportional. Then there is a point here. There's a point about this point. There is no longer any other point they give you after that. You say you don't bother yourself to talk too much. Just call it the yield point. Yield point. Yield point is a point after which little or no force we continue to stretch, give a large extension, even by blowing the thing. It will give very big extension. So after the yield point, after the point beyond which the material yield point, yield point, yield point. Beyond this point, a small or little or no force. Little or no force gives large extension. The weight of the body alone, the weight you already have there, we continue to stretch the material. Big extension until the material breaks at the breaking point. This is the breaking point, B. Again, limit of proportionality, elastic limit, yield point. Beyond the yield point, the body is a little beyond the yield point, a little or no increment in the force will cause a very large extension beyond the yield point until the body necks and breaks. That is the breaking point, the point where the body breaks. The point where the body breaks. Don't forget all these points. They are very important for you. Force extension graph. Don't forget all these points. Limit of proportionality, elastic limit, yield point, and breaking point. This graph can be drawn in another way if delta X or E is on this side and force is on this side. Of course, the shape of our graph will change. The shape of our graph will change. Don't be deceived in an exam. The shape of our graph will change. The shape of our graph will change. So don't be deceived in an exam if you see extension. So now let's go back to the first graph. What else can we know from this graph? We can take the gradient of this graph. The gradient of this graph. What do we need the gradient for? The gradient will give you the gradient of the straight part of the graph, which is rise divided by run. Rise divided by run. Rise, run. Our rise is change in F, which is, we can call it force. So gradient F or delta F divided by delta X or E, which is the same thing as our K. So gradient equals to stiffness or spring constant, which is equals to stiffness or our spring constant. So you see the gradient of F against extension is the stiffness or the spring constant of that spring. Then what about this other graph? Of course, from your mathematics, you know that the gradient of the straight part of the graph will be E or delta X divided by F. So the same thing as gradient here will be equals to not K, but 1 over K, 1 over stiffness. 1 over stiffness or spring constant will be this if it is this against this. We are going to stop here now. For now, we are going to stop here. In our next class, we shall continue by looking at the energy stored in a spring, energy stored in a spring or in a wire. Then we now look at few calculations for practice. So students, good day and God bless. You remember, whatever you don't understand, you know the usual thing, send your email to Teacher Hafiz and it will reply you back with another video custom made for you. Whether it is coming from a past question, whether it is coming from what I just taught you, you know what to do. But first, go through it, go through the video, rewind and get to know all the parts you don't understand. If you don't still understand, send your video and I will reply you back with another video custom made for you. Good day and God bless.